Hi, in this video, we want to talk about the concept of projectile motion. During the course of the video, we'll be looking at the meaning of projectile motion, to talk about the types of projectile motion that we have. Types, that is, the symmetric and the non-symmetric. Then we'll look at the terms associated with projectile motion. The first term we'll look at will be the time of flight to reach maximum height. Then we'll look at the time of flight to reach the range. Look at the meaning of maximum height as far as projectile motion is concerned. And then lastly, we'll talk about the range of maximum horizontal displacement. After that, we're going to be looking at how to derive equations associated with these terms. That is, if we want to find the time of flight to reach maximum height, what equation are we going to use? And then for the other terms too. Then lastly, we're going to be looking at how to solve questions underneath projectile motion. Who is this video for? If you are preparing for this current UTME and WAEC, then definitely you're at the right place. Now, for you to be extremely good in projectile motion, your knowledge in motion in one dimension and vectors will be put to test. That is, you should be able to know the terms we use to describe motion: the velocity, acceleration, displacement. You should all be familiar with them because we are all going to be using these terms also in this topic. Then for vectors, you should be able to resolve vectors into its various components. If you've not seen an earlier video that we made concerning these topics, I would advise you or encourage you to look at that video first and then come back to this so that everything we're going to be doing here will make perfect sense. So what is projectile motion? Projectile motion is simply a motion in two dimensions. That is, we have motion on the x-axis, we have motion on the y-axis. So motion in two dimensions that is strictly under the influence of gravity. When we have motion that is purely under the influence of gravity, and then it is in two dimensions, then we're looking at the concept of projectile motion. Also, in an earlier video, we looked at the concept of free fall, where we said this is an application of motion in one dimension under the influence of gravity. So they are alike in the sense that the only force acting on both of them is the force of gravity. But free fall is in one dimension, while projectile motion is in two dimensions. All right. So we have two types of projectile motion. The first one, we can refer to it as the symmetric projectile motion, while the other one, the non-symmetric projectile motion. For the non-symmetric projectile motion, we have three types. When we throw something horizontally, when we throw something below the horizon, and then when we throw something above the horizon. So we're going to be looking at these two main types, or if you want to count neutrally, look at the four types of projectile motion, and we're going to be deriving each equations that are associated with them. You don't have to cram anything. So once you can see what I'm doing, then definitely I'm sure you'll be able to do everything in as long as you practice them. We start with the first type, symmetric projectile motion. What does it mean for a projectile motion to be symmetric or to be symmetrical? So what we're simply saying is that we want to throw an object, a ball, a missile, doesn't matter. But the point is we want to throw it at an angle. Before now, in previous videos, we've always been looking at how to throw something in one dimension. But this time around, we want to give it an angle. Case in point, this marker, and then I want to throw the marker. So the marker is in my hand, but then I throw at an angle, not just upward now. Now, how can we illustrate this? So let's draw our x and y plane. So we have something like this. And then, okay, so let's use the other part of the problem so we can have more space to talk about this. Okay. All right, so let's say we have a ball at this place. So the ball is there. And then I'm trying to throw my ball So this is my ball. I want to throw it at an angle. Now, if I was in space, once I throw this ball up in one direction, it doesn't even matter. Once I still throw this ball at an angle in space, so let's say I'm throwing the ball like this. What do you think will happen? Because no force is acting in space, this ball will go along this path forever. It goes like that forever. But because my ball, or wherever it is I'm throwing it on Earth or any planet, I might find myself underneath. Instead of this ball to move in a straight line like this, it then moves in a parabolic path due to the influence of gravity. So we have something moving like this in this direction. So this is quite small. Let's see how we can make it a bit bigger. Okay, my x-axis. So, all right. Now this is uneven also. All right, so this is a bit better. So because of the influence of gravity, instead of this ball moving like this forever, gravity will be like, no, I don't want it to go straight forever, but rather come back down. Remember, we're trying to describe what does it mean for it to be symmetrical. Just like we did when we're analyzing free fall. Let's label our points. I can call this point here point 1. Let's call this point 2. Let me call this point 3. Let's call this point 4. And then let's call this point 5. Now, for this projectile motion to be symmetrical, two things must come to your mind. Number one, this is my ball here. It is starting from this level, and then it is ending at the same level it is starting from. Note, I didn't say the same point, but I'm starting from point 1. Of course, my ball will end at point 5. But you can see that vertically now, if I were to plot a graph here and say the value of y here is 20, the value of y here also be 20. So it is starting at and ending at the same level. Now, when that happens, okay, I said two things. So the first one, starting and ending at the same level. The second one, you are throwing at an angle. So if you throw an object at an angle, and then it starts at the same level and ends at the same level it starts with, then we're talking about the symmetric projectile motion. If we want to look at it and see how that helps us or aids us in our analysis, we're simply saying the time it will take us to move from point 1 to point 3. Time to move from point 1 to point 3 will be the same time to move from point 3 to point 5. So if the time taken during the course of this motion from point 1 to 5, let's say it's 10 seconds. Then if this is symmetrical, I'm saying from point 1 to point 3 will be 5 seconds, and from point 3 to point 5 will also be 5 seconds. So if you take this shape and divide by the line of symmetry, you see that it divides exactly into the same opposite half. That's how we refer to it as symmetric projectile motion. Now, for symmetric projectile motion, during the course of our analysis, since from our definition, we said projectile motion is a motion in 2 dimensions. So we want to analyze what is actually happening in both dimensions before combining them. That is, we look at motion horizontally first, and then move on to motion vertically. Remember, if I throw an object at an angle, so let's say this angle here is theta. This angle here is theta. Now, if this object has been thrown at an angle of theta, what happens? My object first is moving horizontally, and also my object is moving vertically. How do I know? Follow the path. At point 1 here, at point 2, where is my object? X, it is here. Point 2 on y axis, it is at this point. At point 3, x, it is here. as point 3, y it is at this point. So you can see we are changing. So my object is being displaced both vertically and also horizontally. So when we want to solve or analyze, then definitely we want to analyze what's actually going on horizontally, and then we move on to what is going on vertically before we can combine. Now, also, we said we're going to be using, or in an earlier video, we looked at terms that we use to describe motion. Terms like acceleration, terms like velocity, terms like displacement. So we're going to be using all these terms or quantities to describe what is actually going on in our projectile motion. In order to aid our analysis so that we don't have to start cramming or what's it called, or having to put so many formulas on our head, we're going to be drawing a table and then we'll analyze all forms of equations that we want to derive from this. So since I have motion horizontally, I can come and draw a table and label this as horizontal motion. Okay, and this should be vertical motion, and then this will be the combined. So since we look at acceleration, acceleration is a vector quantity, displacement is a vector quantity, velocity is a vector quantity. So when we combine what is going on horizontally and vertically, we'll be having the vector itself. Remember, velocity vector has both magnitude and also direction. Acceleration vector has magnitude and also direction. Displacement also vector has both magnitude and direction. So we can use this column to talk about the vector part or the combination of both quantities. Now, horizontally, what are the quantities we want to look at? So first of all, we want to look at initial velocity. So for initial velocity, for the sake of projectile motion, we're going to be denoting initial velocity with V naught. V naught. So this is a vector for the vector part. For the vertical part, we can say V naught of y. For the horizontal part, we can say V naught of x. So this is equal to. So we're trying to look at how we fill in our gap. Projectile motion, horizontal motion, how do we get our initial velocity? That's what we are trying to do. Then the next thing, final velocity. So we can call our final velocity V naught of f. So this will be V subscript f of y, V subscript f of x. Okay. Then moving on to acceleration. So acceleration also a vector. This is equal to acceleration here, so a of y, acceleration here, so a of x. All right. Now, the next thing, the velocity. I say velocity, the position. So position, we can use delta r, okay, as a vector. For this one, delta y. For this, delta x. All right. And finally, time, and also time. All right. Now, this is quite confusing. These are just symbols that we use to name, what's it called? Our quantities that is happening horizontally, vertically, and as a vector. We've been using most of these terms in previous videos. So V naught of x simply means the initial velocity horizontally, only horizontal. Vf of x means the final velocity horizontally. A of x, the acceleration of x. Delta x, displacement horizontally. Then time is time. So same thing here. Initial velocity, final velocity, acceleration in y, delta y, and t. This is purely vertical. And this is the vector combination. Now, for this vector part, it's quite easy for us to fill in. But though most of the questions that we encounter under this projectile motion, especially for secondary school students in JAMB and WAEC and also NECO, they won't ask you for the velocity, find velocity at point 3 or find velocity at point 4. They might not ask that. They might just ask, oh, what is the vertical component of the velocity? What is the horizontal component of the velocity? But just should in case they do, how do you now find the velocity at point 4 as opposed to finding the vertical component of the velocity or horizontal component of the velocity? To just take the velocity on y, take the velocity on x, square them, and then take them under the square root. Or simply, you can just write it as v naught xi plus v naught yj. And you write them as a unit vector. So this is that. Then for this one, same thing. vfxi plus vfyj. For acceleration in y and acceleration in x. Now, I'm going to skip this now. The reason I'm skipping it is, when we're talking about our definition of projectile motion, we said only one force is acting, and that's the force of gravity. So if only one force is acting, that is the force of gravity, that means acceleration in y will simply be our acceleration due to gravity, g. Acceleration in x, we're going to look at it when we're analyzing, but we'll come to a conclusion that acceleration in x is actually 0. So how do we now find the acceleration vector? Of course, it will just be g, but if we want to write it in form of our unit vector, we can say ax of I plus ay of j. Delta x, delta y. So this will be delta xi plus delta yj, and tt, so time is the same for all forms. All right, so like I said, so let's look at what is actually happening horizontally now, purely horizontal. So let's see, what can we say? Now imagine we were to shine a light from above. I want to shine a light at this. Imagine, thank God most of us were all football fans. Now imagine someone playing a free kick from this point 1 up onto point 5. Place it from the same level, and then it ends at the same level with the starting level, but obviously not at the same point. Now, if I were to be looking at it from the very top, let's say from this angle, what will I notice? I'll notice that at point 1 here, at point 1, okay, even before we talk about that, let's try and resolve our velocity vectors at different points. So this can make perfect sense. At point 1 here, I have a velocity vector that is tangential to this part. Tangential, this can be my velocity vector, tangential, that is touching this point at just a single part. Now this velocity vector, I can call it V naught, just like I've said in my table. And since the vector quantity, let's do our arrow diagram. Now from resolution of vectors, I know that if I resolve this vector, or I can resolve this vector into two components. The first one will be on the x-axis, V naught of x. The second one will be on the y-axis, V naught of y. And this V naught of x, I can call it V naught cos theta. This V naught of y, I can call it V naught sine theta. How do we arrive at this? We looked at it when we were talking about the concept of vectors, how we can resolve vectors into its various components. We said for the horizontal parts, we represent it with V naught cos theta, and for the vertical parts, we represent them with V naught sine theta. All these things have been resolved from my velocity vector, V naught. If that doesn't make sense, imagine I were to be spinning this marker in a circular path. Now, what happens? And I'm spinning it fast. So what happens the moment I just move my hand? Wherever this is, the part or the point, maybe this is recorded, and then I stop the recording. Now, wherever it is, my marker stops in my hand. By the time I release my hand, it tends to fly in that direction. The reason why it is not flying when my hand is holding it is because there's a force or there's a grip on this marker. So once that grip loses, this marker moves tangentially or moves according to tangential velocity in that same path. So that's what we have here. At this point, this ball simply wants to go straight forever. But because of the influence of gravity, so this velocity, instead of it to go straight, it is moving in this parabolic path. So at this point, I have a final velocity and instantaneous velocity. At this point 2, I have a velocity. At this point, I have a velocity. This point, velocity. This point, velocity. That's why we had to label our points, so we can resolve each velocities into its various components. All right, so at point 2 also, I have velocity that is tangential. So in this part here, okay, this is my angle theta. So this is, I can call this Vx, I can call this Vy. At point 3, I have a velocity vector moving in this part. I don't have any hop. You can see that at point 3, my ball is no longer moving upward. It's just moving towards the right. So this one, I can call it Vx. Okay? Vx3, Vx2. Now at this point here, where's my velocity vector? So also tangential, like this, in this part. So this time around, I have an x-axis here. So this is theta, this is down. So this one I can call it Vx4. So this is Vy4. Then at point 5, again, tangential. So this is my angle. I can call this Vx, and then I can call this Vy. All right. Now, after resolving, imagine I were now to shine the light at this particular point. What does it, or what will I be seeing? At point 1, imagine you're at a very high place, and then you are looking at a ball being fired at an angle. At that high place, definitely, you won't see the ball rising up. All you just see is the ball moving towards a particular part. And from what you can see here, at point 1, my Vx is moving in one direction. So at point 1, at this point here, I can see my ball is moving in this direction. So let me call this point 1. All right. At point 2, what direction is my Vx moving in? Still moving towards the right. So point 2, still moving towards the right. So this is point 2. Point 3, what direction is it going? Still towards the right. So at point 3, still towards the right. So this is Vx2, this is V naught of x, this is Vx3. Correct. At point 4, what direction is my Vx still moving in? Still moving towards the right. Okay. So this is Vx4. At point 5, what direction is my Vx moving in? You see that it is still moving towards the right, Vx5. Now, if you look at our velocity horizontally now, only horizontal, the first question that wants to come to our mind, V1 moving towards the right, V2 towards the right, V3 towards the right, V4 towards the right, V5 towards the right. Now, is there any force acting on these velocities? Is there anything pushing or pulling it to propel it to move in this direction? The answer is no. And now, just like Newton's first law, an object at rest wants to remain at rest, or an object at constant velocity wants to remain in constant velocity. Now, since there's no force pushing or pulling these velocities or this ball, pulling to the right or pulling to the left, then what is the conclusion we can come to? We can say our velocity horizontal is constant. What does constant velocity mean? It means V1 must be the same thing as V2. V2 must be the same thing as V3. V3 must be the same thing as V4. And V4 must be the same thing as V5. That said, then we can now come to a conclusion and say V naught of x must be equal to Vx of 2, must be equal to Vx of 3, must be equal to Vx of 4, must be equal to Vx of 5. Now, what do we know from motion in one dimension? Once velocity is constant, then it must mean that acceleration is equal to 0. Now, remember, we talked about motion under constant acceleration. where we look at our equations of motion. The first equation of motion we looked at, we talked about the V final must be equal to V initial plus AT. V final squared must be equal to V initial squared plus 2A delta x, and delta x must be equal to V initial t plus half AT squared. We looked at this equation of motion when we're talking about constant acceleration. Now, velocity is constant. And we said when velocity is constant, then it must mean that my acceleration must be equal to 0. If acceleration is equal to 0, if I put 0 here, then the equation I can derive from this will simply be V final must be equal to V naught. And what do we say our V naught is, or V naught of x, since we're talking about horizontal now? So V naught of x is simply V naught cosine theta. So V naught cos theta, which was the same thing we said. When there's no force acting on velocities horizontally, then it must mean the velocity at point 1 must be equal to velocity at point 2, must be equal to velocity at point 3, 4, and 5, which is what our equation is denoting. All right. Now for the second equation, if I put 0 here, everything here automatically becomes 0. So again, V final must be equal to V final squared must be equal to V initial squared. Same thing as equation 1. No changes. I'm just squaring this first one, and then it results in the square of the other one. What about this? Delta x. If I decide to put 0 here, everything here becomes 0, and then we have delta x must be equal to, again, V naught cos theta times time. So for us to find anything horizontally for all types of projectile motion, what are the equations that we need? We don't need this again. This is no longer valid for projectile motion horizontally. What do we need? This and this, these two equations. So the first one, V naught of x. So we already said this is equal to V naught cos theta. So V final is still equal to V naught cos theta. Our acceleration is equal to 0. Why is it 0? Because purely on the horizontal level, there is no force acting on it. And if there's no force, then our object can't accelerate or decelerate. So acceleration is equal to 0. What is delta x? Delta x is simply equal to V naught cos t, cos theta t, and then time. So time is time. So find time using our equation. So basically, they'll give us any 2 or any 3, and then we use that to find time. All right. I hope this makes perfect sense. Now, we want to look at what is actually happening vertically. What is happening vertically? Now, for vertically, instead of looking from this angle now, we want to look at this motion from this side. From this side here, if I look at it from this side, what can I say? Or what will I be able to say? And then we can come to another set of conclusion and see what we can derive from there. All right. So vertically now, I want to look at my light from this angle, from this angle, from this angle. Now, what do I see? So if I look at it from point 1, my velocity vector, where is it going to? It's pointing upward. You can see Vy, V naught sin theta is pointing upward. So at point 1, so this is point 1, so I can say I'm moving up. At point 2, what is happening? Still moving up. So this is point 2, I'm moving up. At point 3, do I have any velocity? Definitely not. I don't have any velocity on the y-axis. So what's my velocity at the y-axis? Is equal to 0. So I don't have to denote it here. What about point 4? What's happening to my velocity vector? It's pointing downward. So point 4. So this is point 1. This is point 2. So point 4 pointing downward. Okay. At point 5, what's happening to my velocity? Still pointing downward. So at point 5 here, my velocity is pointing downward. Now, this reminds us of free fall. And what are the equations we said we use when it comes to free fall? So we said we use these equations. So V final must be equal to V initial minus GT. V final squared must be equal to V initial minus 2G delta Y. And then delta Y must be equal to V naught T minus half GT squared. Now, because I'm firing this ball at an angle, then I have to tweak this formula slightly. So what do I want to tweak in it? Just add the inclusion of my sin theta, and also sin theta. Remember, since this ball is moving upward, going up and also coming down, we have a force acting on this, and it is the force of gravity, only the force of gravity. So definitely, I have acceleration, so I can't turn G to 0. G has a constant value, either 9.812, or we use 10 meter per seconds squared. All right, so we're tweaking this to come and use for projectile motion. For projectile motion, we can simply say V final must be equal to V naught sin theta minus GT. V final squared must be equal to V naught sin theta minus 2G delta Y, and delta Y must be equal to V naught T sin theta T minus half GT squared. Now, when we want to fill this, how do we now get or calculate our initial velocity on Y? So we come to use any of these equations. We can no longer use this because this has not been tweaked. Our ball is being fired at an angle, not just the classic free fall that we have. But if you use any of these equations, then anything you're looking for underneath this, you're going to find it. Remember, for the horizontal, we only have one equation, which is this equation, and a statement. Initial velocity is always equal to the final velocity horizontal as far as projectile motion is concerned. But if we want to find the displacement horizontally, then we can come here and use delta x is equal to v naught cos theta t. All right. Now, I hope that makes sense. Now, since we are talking about symmetric projectile motion, we have access to 3 other equations. Now, note, all these equations we derived earlier, aside from the general ones, the statements, the equations, everything is the same thing we use for all other types of projectile motion. But this next set of equations we want to talk about is only restricted to symmetrical projectile motion. And the first one we want to look at is our maximum height. Now, mainly looking at our graph, you can see that the maximum height of this graph or of the object or the ball, if the ball is moving from this point, will be at point 3. Remember, we said this is point 3. Now, at point 3, point 3 happens to be my maximum vertical displacement, delta y maximum. But in projectile motion, we refer to it as the maximum height. So at point 3 here, I can say delta y is equal to h max, maximum height. Now, what are the things we can say that is actually happening vertically? What do I know that is happening at point 3 vertically? I can say that at point 3, my velocity at point 3 is equal to 0. If I'm starting from point 1 and I'm ending in point 3, then velocity at point 3 will happen to be my final velocity. Now, if you just ask me what is the final velocity vertically at point 3, I'll tell you it is equal to 0. Because at 0, at point 3 here, I can see that my ball is no longer moving vertically. So it must mean it is equal to 0. Just like taking this marker and throwing it up. By the time you throw it up, and then this marker gets there's a maximum place it gets to where the velocity becomes zero before it starts falling freely again. So at this point here, we can say Vy must be equal to zero. Now, if Vy is equal to zero, since I'm analyzing vertically now, I can go to any of these equations of motion and try to see how I can relate my velocity and then my h max together. If I try to use equation 1, V final, I know it is equal to 0. V initial will be given the firing angle and then the initial throwing speed. So definitely, I should know how to get this. G constant, T, we don't know, but that's not what we're looking for. So we can't use equation 1. Equation 2, I know this. This could be known. Delta Y, that's what we're looking for. So we're using equation 2. So we can say Vf squared is equal to V naught sine theta all squared minus 2g delta y. Remember, we said at point 3, at point 3, okay, Vy is equal to 0, and then delta y, we want to refer to it as h max. So we can now reshuffle, and then everything here will be equal to 0 because by the time you square 0, it will still give us 0. Then bring this to the other side. We have 2g. So instead of writing delta y now, to write h max or maximum height must be equal to v naught squared sine squared theta. And then divide both sides by 2j. So h max will simply be equal to v naught squared sine squared theta, everything divided by 2j. So this is another equation that we can add to our list of equations for symmetrical projectile motion. If you use this equation for non-symmetric projectile motion, then you are going to be answering a different question entirely. This equation is only valid if the projectile motion is symmetrical. And this is the H max, the maximum vertical displacement of the ball or the object along the projectile path. So V naught here is the initial velocity, we're squaring it. Then sine square theta, let's say we're given an angle of 15 degrees. So we'll just simply say sine of 15, then everything all squared. Press that in your calculator. G is constant, either 9.812, wherever, or 10 meters per second squared. By the time you press everything inside your calculator, you're able to find the value of your H max. All right. Now moving on to the next term that we said, the time of flight to reach the maximum height. Time of flight to reach maximum height. So it means that if I want to move from point 1, or if the object wants to move from point 1 to point 3, it has to do that with the inclusion of time. So if we want to time it, how fast is it going to move from point 1 to point 3? What equation can we use to determine that? All right, so now we're going to be going back to our equations of motion. So let me just drop this place up so we can have space to work in. Now, earlier on we used equation 2, this second equation. So can we use equation 3? Yeah, but then, like, since this is t to the power of 2, this is another t, and then we have delta y here. So we really don't need delta y for this. We only need to know the time it's going to take to get to maximum height. So I'm going to come to use equation 1 instead. Of course, we can use equation 3, but that's a bit lengthy, and then we have to make something so with the formula, but let's just use equation 1 and see how easy this will be. So for equation 1, we have Vf is equal to V naught sine theta minus Gt. Now, there's something we need to note. The t value we're using here will simply be from point 1 to point 3. Remember, point 3 is my maximum height. And one from our definition of something symmetrical, the time it will take me to move from point 1 to point 3 will definitely be the same time it takes me to move from point 3 to point 5. So if I can know from point 1 to point 3, that's the time of flight from maximum height. If I want to know the time of flight for the whole course of the motion, then I'll simply multiply it by 2. Okay, so let's move on. So V final from this, okay, I can write 1 to 3 here. Okay. Now V final from 1 to 3, V final here is equal to 0. So I can say 0 is equal to V naught sine theta minus GT 1 to 3. Bring this to this side, we have GT is equal to V naught sine theta. Okay. And then make T the subject of the formula. So T1 to 3 will simply be V naught sine theta all over G. If I simply want to find the time of flight for the whole course of this motion, then what do I want to do? So T1 to 5 will be equal to 2V naught sine theta all over J. So 1, 2. That we have 3 equations that we talked about as far as symmetric projectile motion is concerned. All right. The next one we want to look at will now be the maximum horizontal displacement, or what we refer to as the range. What it simply means is you take a ball, you throw it. Maybe the first time you throw it, it dropped at this point. From this point to this point, I can call that delta x. So let me rub this place off so that you see what I'm trying to say. Okay. Okay, so from this point to this point, we can call it delta x. Now, you take the same ball, you throw it again, you see that, okay, maybe the ball dropped at this point now. So from this point to this point, we also have delta x. So I have delta x at every point. But one is always so special. The delta x from the final point or the ending point to where I'm starting from. So this delta x, we can see delta x maximum horizontal displacement. And this delta x maximum, we otherwise refer to it as the range. How do we calculate range? Or how do we solve for range? In order to solve for range, we have to look at what is actually is going on at point 5 that we can determine vertically now, just vertically, and then we'll move on to the horizontal part. Vertically at point 5, what do I know? At point 5 here, I can see that my delta y will be equal to 0. I'm starting here, delta y is 0 here. Then increase till it gets to 3, which is the maximum. Then comes down, and get to 5, which is again the minimum. So at point 5 here, my delta y is equal to 0. My delta y is equal to 0 at point 5. Then I can come to this third equation of motion and set this to be equal to 0 and try to find the value of my t. Remember, this t I will now be talking about will now be t from point 1 to point 5, not point 1 to point 3. Okay, so let's see what that means. All right, so now delta y, so we say delta y is equal to 0. So 0 is equal to V naught sine theta t minus half gt squared. If I decide to divide both sides by t, so I'll have 0 is equal to V naught sine theta minus half gt. Take this to the other side, we have gt over 2 is equal to V naught sine theta. Okay? V naught sine theta. Make t the subject of the formula. So multiply by 2 first. We have gt is equal to 2V naught sine theta. What do we do? Divide by g, or divide both sides by g. So t1 to 5 is equal to 2V naught sine theta all over j. Remember, we arrived at this equation when we multiply the time of flight by 2 earlier on. Okay, so now we're going to stop for now. So this is equation 1. Now, since we're trying to look for the maximum range, we'll now come here. How do I find delta x here? Delta x is simply equal to V naught cos theta t. But if I'm talking about t from 1 to 5, then this delta x will now be the range. So I can say r here, or r will now be equal to V naught cos theta T1 to 5. Now, what's my T1 to 5? It's giving us 2V naught sine theta over J. So I can just come here and write that. So R will be equal to V naught cos theta. So write this in the bracket. 2V naught sine theta all over G. Okay, so if I decide to open the bracket, you'll see that R is equal to V naught, okay, V naught squared. Okay. Let's write 2V naught squared. Okay, we have the cos theta sine theta all over G. Okay, now we can't leave our answer like this. From trig identity, we know that when we have two, or when we have cos theta, 2 cos theta sine theta. When we have this, we can simply write this from trig identity as sine 2 theta from trig identity. Once we have 2 cos theta sine theta, I can simply write it with using my sine 2 theta. Now, what do I have here? I have cos theta sine theta, I have 2. So what can I do? Can I write it and say sine 2 theta? Obviously, yes. So I can now come and say R is equal to V naught squared sine 2 theta, everything divided by J. And this is the formula for our maximum horizontal displacement or range. Now, this formula range is quite important. Why is it important? Imagine I want to throw this marker from this point here to where this red one is. There are two things that will aid me throwing this in this accurately. I can either throw with a very fast speed. Maybe I throw with 20 meters per second and then it is ending here. If I increase it 25 to end there, increase it 30, end there, increase it 45, end here. Now, maybe if I increase it to 50, then it will touch this one per se. That's one, what's it called? That's one scenario. The flaw about that scenario is that as human and even machines, there's a limit to your throwing speed. Doesn't matter how strong you are. By the time you get to your limit, then you can't increase your velocity any further. That means we need the possibility of attaining accuracy depends on one factor, the throwing angle, which is theta here. And again from trig, we know that the sign of any value, the sign of any value, or the maximum sign, or the maximum value rather, sorry about that, the maximum value of the sine or cosine of any value is always equal to 1. So if I want this range to be maximum, what would my theta have to be? Remember, we know from trig that sine of 90 is equal to what? 1. And if everything here is equal to 1, then definitely my range is at its maximum. How do I make everything here to be equal to 1? It means theta must be equal to 45 degrees. Now, if theta is equal to 45 degrees, then 2 times 45 gives us 90, and sine of 90 will give us 1. This is a trick question. Sometimes you might be told that you should find the maximum range. Maximum range. And they won't give you theta. Since they've said maximum range, then definitely you assume the theta will be 45 degrees. So that will ease your solving. All right. Now, this is everything we want to learn about our symmetric projectile motion. Moving on to the non-symmetric projectile motion. For non-symmetric projectile motion, the first type we'll look at will be the horizontal, or throwing an object horizontal. So let me try and clean this part here. Let's try and clean this part. Now, for the non-symmetric, the first one we want to talk is horizontal firing or throwing. Okay. First one we want to talk about is when we fire an object horizontally or when we throw an object horizontally. The classic example, taking a gun and then firing straight. So let's say we have a gun like this, and then we want to fire a bullet from its mouth such a way that it moves like this. Now, what happens to this bullet if it was in space? You discover that this bullet will just be going straight for eternity. But due to the influence of gravity, instead of this bullet to move in a straight path, this time around, this bullet will move in this path, the parabolic path, till it touches the ground. So let's assume that this is the ground here. So this is our ground. Okay. So this is the path in which the bullets will move. Now, what can we say? What can we say? Again, let me call this point 1. Let's call this point 2. Let's call this point 3. Velocity vector that I have there, I have one moving like this, tangential to this part. Here I have it moving like this in this part. Here I have this moving in this part. So this is only Vx or V naught of x. Okay. V naught of x, V of y, again, Vx and Vy. Now, what are the things or what are the conclusions we can come to at this particular point? For this one, when we fire something horizontal, purely horizontal, like I said, the gun, when we fire the gun straight, what are the things that we can denote or what can we deduce from this? At first, at point 1, I only have a velocity to the x. I don't have a Vy. At point 2, it is tangential or inclined at an angle. I have my x, I have my y. At point 3, I have the x, I also have the y. So what can I say? From our first table, from our equations, we said our initial velocity, v naught, must be equal to v final. Remember when we shined our light from the top. So this is also true. But this time around, what is my firing angle? If I'm firing something straight, then theta must be equal to 0. If theta is equal to 0, then I can say V final must be equal to V initial, because cos of 0 will simply be 1. Delta x must be equal to V naught of t. So these are the two equations I want to use horizontally. For vertical, so we say V final is equal to V naught sine theta minus gt. V final squared is equal to V initial squared minus 2g delta y, sine theta, V initial squared sine theta, so everything squared minus 2g delta y. And lastly, delta y is equal to V naught t sine theta t minus half gt squared. Now, if my firing angle theta is equal to 0, if I put 0 here, sine of 0 is 0, so everything here cancels out. So I can say, or my first conclusion can be that Vf must be equal to minus gt. Okay. Again, put everything here 0. If everything here is 0, what can I say? I can say V final squared must be equal to minus 2 g delta y. And lastly, if everything here is equal to 0, then delta y must be equal to minus 1 over 2 gt squared. So if we're dealing with this type of projectile motion, where what's it called? We're firing straight, straight. Then we don't need to impute our cositheta sin theta because it will be 0. So we can just come use either of these statements or this equation or 1, 2, or 3. So don't bother about this one again. So this is no longer valid for this type of projectile motion. You just come here, Vf is equal to minus gt, Vs square equals to minus 2g delta y, or delta y is equal to minus 1 over 2 gt squared. All right. Now, the third type of projectile motion we want to look at is when we're now throwing something downward. We are throwing something downward. So downward like this. But before we move even to that, if you are confused about why is this negative sign, or why am I having a negative sign here, negative sign, and negative sign here, you just go to your what's it called, to your graph, to the sketch. G constant 9.8. Time can't be negative, it's always positive. Huh? But G pointing downward, so it is negative. Now, the way equations work is that the left hand side must be equal to the right hand side, both in magnitude and direction. Now, if G is negative, pointing downward, so what should be the sign of our final velocity? Since final velocity is always pointing downward, then it will always have a negative value. So when you multiply a negative value and a positive value, the answer will be a negative value. Look at this point here. V final vertically pointing down. At this point, V final vertically still pointing down. So it will have a negative value, which is what we said here. For this one, G is negative, which you said there. Delta y at this point, pointing down. We're starting here, and then this is my final position. So coming down, so negative. Now, if this is negative and this is negative, multiply them together, it turns a positive value. By the time you square any answer or any value, whether it is negative or positive, it will definitely return a positive value. So this equation is also valid. For this one, square this. If I square this, to square a positive number is still positive. G is negative, and then delta y at any point in time, delta y from this point to this point is negative because it is pointing downward. So by the time everything, we resolve everything here, so that this negative sign will also apply to this other side. So the signs are well accounted for. Just come and put in your value. Put in the value of G to be positive. This is the negative sign already accounting for our acceleration direction being negative. But we said all these things underneath free fall and motion in one dimension. So I hope this makes perfect sense now. All right, so for the third type of projectile motion, below the horizon, So basically, we have a ball here, and then we want to throw. So maybe the ball is okay. The ball is somewhere here, and then we want to throw it in this direction. We want to throw the ball in this direction. Okay, in such a way that if not for the influence of gravity, this ball will keep on moving in this path till it touches the ground. But because of the influence of gravity, this ball won't move in this path, but rather move in a parabolic path. Okay, so we have our angle. So let's call this angle. Let me try and draw this perfectly. Okay. Okay, so instead of moving, okay. All right, so this is our ground level. All right, so now I have my train speed. So this is v not vector. Now for this, so let's call this alpha. And again, let's remember our point. So this is point 1, then this is point 2, and then this is point 3. For point 1, my velocity potential like this. So for point 2, also tangential like this. I have one coming down, I have one going here. For point 3, also tangential like this. Okay. All right. Okay. So now, what are the things that I want to denote from this part? The first one, note the angle I'm writing here. When we throw something down, this angle we are given here, we are calling it alpha. Now, the first thing you want to do for this type of projectile motion is to get theta. And how do we get theta? Theta will always be equal to 360 minus alpha. How do we arrive at this? If you have conversant with angle of elevation and depression, you know that when you're looking downward, the angle of depression is not this one, it makes with the, what's it called? It's not this one, it makes with the imaginary horizontal, but rather this angle here. So theta. Because if we were to complete our triangle, this angle here will now be the same thing as this angle at this particular point, not this one on top. The first thing we want to do is to change this alpha to theta. And how do we change it? Since this is always in the fourth quadrant, if this is in the fourth quadrant, remember, we have four quadrants like this. So this is in the fourth quadrant. This is the angle that we're given. So this one, this remaining angle here will just simply be 360 minus alpha, so minus alpha, and then we're having our remaining value. So we're not using alpha here, we're using what's it called? We're using theta. So that's the first thing you want to do. And then after this, then we'll go to use our equations, our normal equations. So this one doesn't have any special, any other special addition to it, except including or using the proper angle. So we can say our V naught initial is, or V final will simply be V naught cos theta, and then delta x will simply be V naught cos theta t. So that's for the x-axis, and then for the y-axis, so we're using our equations of motion. But remember, this should be theta, not alpha, that we're given originally in the question. Now moving to the last part of projectile motion that we have. Last part of projectile motion that we have. So let's claim this part and see where that leads us. All right, so for the last part, when we're throwing something above the horizon, the horizon. So basically we have maybe a building or a tower here, and then we want to throw this ball at an angle of theta. So normally instead of this ball to go like this forever in space, this ball will move in this part and then fall straight back. So let's assume that this is the ground level. All right. Now, for this one, you can get confused easily and think that, okay, maybe this is a symmetrical type of projectile motion. I'll say yes and no. This can be symmetrical, but let's label our point first. So let me call this point 1. Let me call this point 2. Let's call this point 3. Let's call this point 4. Let's call this point 5. And then let's call this point 6. If we're only concerned about motion between 1 and 5, between 1 and 5, then we can label it or we can call it projectile motion. We can see we're starting at point 1, but we're ending at the level below it. So point 1, point 6. So this is not symmetrical. So, but for this, there's no special case. Just to know that if we are going to be using any of our special formulas, we can't use it for any of the three places that we talked about. So for this one, yes, we have a maximum height. But for us to calculate our maximum height, we simply get the height between point 1 and point 5, and then we add it to the height of this towel here from the ground. So that's how we analyze questions underneath this. The next thing to do now is look at questions underneath projectile motion. So for our first question, we're told that an arrow is horizontally projected from the top of a towel with an initial velocity of 15 meters per second. So we want to write our initial velocity v naught to equal to 15 meters per second. Then we're told that the time of flight, the time it takes to reach the ground, was 7 seconds later. So after the ball was or the arrow was projected from the top of the towel, it took a total of 7 seconds to reach the ground. Now we're asked to calculate the height of the towel. All right, so one thing we know is that before we can analyze our question, we want to determine what type of projectile motion we're talking about. Is it the symmetrical or the non-symmetrical? And the quick or the fastest way to know whether it is symmetrical or not is to do a sketch. Come from here. So if we're throwing something horizontally from the top of a tower, so that should tell us that okay, this is not a symmetrical projectile motion, but rather a non-symmetrical projectile motion. Which one will it now be? Will it be above the horizon, below the horizon, or purely horizontal? So as the name implies, or as the question has implied, so it is thrown purely horizontal. So if it's horizontal, then we know that theta must be equal to 0 degrees. Okay. Then also we are told that the we have to find the height. Okay, so this is the height we're looking for. So let's just quickly sketch. So if this is my towel, then it means this arrow, let's assume that the arrow is here and then it has been fired straight. It has been fired straight like this. But because of the force of gravity, it will move in this part. So it's going to take 7 seconds. So you can see this is purely horizontal. So our theta is equal to 0. Now, what do we do or how do we find the height of our towel? Now, if you look at all the equations that we are concerned with or that we have, we know that we can look for delta y. So how do we find delta y? Delta y will simply be from this point here, remember, vertical displacement. So if I'm starting here and I'm ending on the ground, so delta y is simply from this point to this point. So this is delta y. And you can see that delta y is pointing downwards. So delta y will definitely have a negative value. But the question is not asking for delta y. The question is asking for the height. So, and how do you calculate the height? So the height is from the ground there up to the top of this tower. So we'll just find delta y and take the absolute value, and that will be the height of this. Now, if you are confused about the equations you need to use here, then you need to write your equations of motion on the y-axis for a projectile motion that is projected horizontal. So remember, we gave about 3. We said the first one we'll be using is BF, V final, must be equals to minus GT. But we're not looking for the final velocity, and we are given the time, so we can't use this. The second one we talked about, we said V final squared must be equal to minus 2g delta y. Now we're looking for delta y, but we don't have the final velocity, so again we can't use this equation. And lastly, we know delta y is equal to minus 1 over 2 gt squared. Now we know time, we're looking for delta y, so definitely this is the equation that we want to use. So we just plot everything in. We know that delta y will be equal to minus 1 over 2 g. We're told to take g as 10 meters per second squared, so we take times 10, then times what's our t? 7 seconds, so this is 7 squared. Okay, so 2 can go in 10, that's 5 times, and 7 squared is 49. So we have minus 5 times 49, and minus 5 times 49, that gives us so this is minus 225 meters. So delta y is minus 225 meters, just like we said. So delta y will always have a negative value. So the height now of the tower, because height can never be negative, just like me asking for how tall you are, and then you're telling me minus something. So I will feel maybe you are going backwards, or your head is on the ground, and some other kind of lame jokes that isn't funny. Okay, so taking the absolute value here, so the height will simply be equal to 225 meters. All right. So for our second question, we're told that a ball is projected horizontally from a height of 20 meters above the ground with an initial velocity of 0.4 meter per second. We're asked to calculate the horizontal distance moved by the ball before hitting the ground. All right, so just like we did in the previous question, we're going to try and sketch what is actually happening, then write down our parameters and see how best we can solve or have our solution. So uh, the towel, okay, so let's assume that the height we're given, so this is 20 meters. Okay, let's write that properly. This is 20 meters. All right. Now, the ball is somewhere here at an height of 20 meters and it is projected horizontally. So, normally this is supposed to go straight, but because of the influence of gravity, it is going down like this. Now, this is what we're looking for, the distance between the foot of this height and then where it's landed. So, that's delta x. And how do we find delta x? When we have a projectile motion that is fired horizontally. So we can say that our delta x will simply be equal to, sorry, let's write this properly. Delta x will be equal to u, normally, okay, so this is v naught. Normally we're supposed to use cos theta here, but since we know that theta is already 0, it will just be v naught t. All right. Now, what are the parameters we're given? Delta y is equal to negative 20. I is it negative 20? Remember the previous solution or the previous question. So what we did, we got our delta y for this case. We already said it's always 0. If it is always 0, then the height will be the absolute value of delta y. So initial velocity v naught is given as 0.4 meter per second. Okay, so I think that's all. And then we're given j to be 10 meter per second squared. Now, for us to find delta x, since we know v naught, but we don't know t, so we can't use this equation yet. So we have to look at what is actually going on vertically. If we can get time vertically, the same time, imagine this ball was to be falling freely from this height here downward. If it's going to use 10 seconds to fall from this point to this point, to the bottom, the same way is going to use 10 seconds to move from this point to this point. That's why when we're analyzing um, uh, our formulas, we said the time is the same for both vertical and horizontal. So that said, then we can use the third equation that we used for vertical approaches. So we can say delta y will simply be equal to minus 1 over 2 gt squared. We use that to get t, then we'll come and slot it in this side and get our delta x. So delta y, we already said it is minus 20, so equal to minus 1 over 2 times 10 times, so okay, t squared. So minus 20 is equal to minus 5 t squared. Okay, and then we divide both sides by minus 5. Dividing both sides by minus 5, t squared will simply be equal to minus 20 divided by minus 5, and t squared will be equal to 4. So the negative cancel out negative, and then we have 4. Now, if we had used positive side here, then we'll have been having a negative number around this place. And you know, when you press in your calculator, the square of the negative number is always going to return what's it called, an error, because it is a complex number. So you have to appropriate the sign when you're solving so you don't get stuck on the way. Okay, so and the square of 4 t squared, so t will be plus or minus 2. So we already know that this is physics, time can never be negative. So we only take the positive value, that is just 2 seconds. And then we can come back here and say delta x must now be equal to 0.4 times 2, and 0.4 times 2 will simply give us so 0.4 times 2, so this is equal to 0.8 meters, 0.8 meters. So this is delta x. So you can see that once we can know the type of projectile motion we're dealing with, then it helps or aids our solving. We're able to solve questions without worrying about which equations or which formulas to use. Let's move on to the third question. So for our question 3, we're told that a body is projected from the ground at an angle theta to the horizontal with a velocity of 30 meters per second. It reaches a maximum height of 11.25 meters. We're asked to calculate the angle, the time taken to reach strike the ground rather, the range, its velocity, 2 seconds after projection. So like we always do, the first thing is to sketch. So sketching this, we know that projectile motion will look like this. So we're throwing the body at an angle theta to the horizontal. So the body is coming in this direction, falling at the same level as the starting point. So this is simply telling us that this type of projectile motion is a symmetric projectile motion. So we want to write our parameters, the parameters we were given. So V naught, we know that V naught is equal to 30 meter per second. Okay. The maximum height, H max, is given as 11.25 meters. Then, okay, so since we're not given J, so we're going to assume J to be equal to 10 meter per second squared. All right, now, since we're looking for the angle, we can use the formula for our H max. Since we know what the H max is, so we can try to equate the formula for our H max and then make theta the subject of the formula. Remember, we said H max is simply given as u squared sine of v naught squared. So let's just write that properly. V naught squared sine squared theta all over 2j. So we know what V naught is, we know what J is, we know what H max is. We can simply make theta the subject of the formula, and then from there we can get the value of our angle theta. So moving on, so if we try to make theta the subject of the formula, first of all we try by cross multiplying. So we can say, so for the sake of writing further, I'm just going to be writing H instead of H max so that we don't get or make the solving look much more complex. So we can say H times 2J. Remember, H is denoting the maximum height, would be equal to V naught squared, V naught squared sine squared theta. Okay. Now we're trying to make theta the subject of the formula. So we divide both sides by V naught squared. So let's write that one here. So we can say sine squared theta will simply be equal to h times 2j divided by v naught squared. Okay, and then remember sine squared theta is simply as saying sine theta, then everything all squared. So sine squared theta, we have sine theta all squared is equal to h times 2j all over v naught squared. Now, if I want to eradicate this square, I have to take the square root of both sides. So square root of this, then square root of this. Square root will cancel out the square. We will simply have sine theta is equal to the square root of h times 2g all over v naught squared. And theta finally will be the sine inverse of everything that we have here, h times 2g all over v naught squared. So we can start putting in our values. So sine inverse of h is given as 11.25, 11.25 times 2 times 10 divided by 30 squared. So we can write everything or put everything inside of our calculator. So using our calculator, we have so I'm going to be doing everything once here so that I can bring out the answer once and for all. But it's something you can actually press on your hand to see if you're actually following from the start. So our theta, the value of our theta after taking our value will simply be equal to 30 degrees. Remember, if you are using a scientific calculator, uh, multiply this first, divide it by the square of this. Make sure you square this 30 squared, that's about 900. So what's it called? Divide it by this and then take the square root before taking the sine inverse. And when you are doing all this, remember not to truncate anything, otherwise your values might be above 30 or below 30. Okay, so theta is equal to 30 degrees. Then we can move on to the second part of the question. For the second part, we have to find the time taken to strike the ground. So if you remember, when we were trying to prove our equations, we talked about two times as far as symmetric projectile motion is concerned. The first one we talked about was the time it would take to reach the maximum height, which is this point here, and also the time it would take to reach the maximum range. So the question is asking for the time taken to strike the ground. So this range here, so this point here is what we're looking for. So we'll simply take our time of flight and then we'll multiply it by 2. So t, so I can say t1 to 5, just to what's it called? Mirror what we've been talking about in our proving. So t1 to 5 will then be given as 2 v naught sine theta all over G. Okay, so we know the value of theta, 30 degrees. We know the value of V naught. What's V naught? 30. We know the value of G, 10. So slot everything in. So T1 to 5 will simply be equal to 2 times 30 sine 30 all over 10. Okay, so 2 times 30 sine 30. So 2 times 30, T1 to 5 times 30 will simply give us 60 times sine 30 should be 0.5, everything divided by 10. So, and then our final answer will be equal to 3 seconds. We'll press this in our calculator. All right. Now, the next thing we want to do is to find the range. The question asks us to find the range. So let's try and clear this part so we can have enough space to work with. Okay, so for the range, first we start by writing our formula. We know that the range is simply given as v naught squared sine 2 theta, everything divided by g. So what don't we know? We know the value of theta, we know the value of our v squared, we know the value of g. So this is simply a straightforward answer. So v naught, that's 30. Remember to square it. Sine 2 times 30. So remember, this is 2 theta. So you are multiplying by 2. So G is 10. Okay. So again, by the time we do everything here, so we know that this is 900. By the time we square 30, 2 times 30, that gives us sine 60 all over 10. So an R will then be equal to. So we press everything inside of our calculator, we discover that our range will be equal to 77.94 meters. Okay, and finally, its velocity 2 seconds after projection. So this is, like I said, when we're proving, this is the pitfall where exam bodies usually wait for students, because the velocity they're asking for is not just the vertical or horizontal. This time around, it is the vector component. So you might solve this, and then you only solve for the vertical velocity or the horizontal component of the velocity and think you are done. Actually, you are not. So you still have to find the vector or the combination of both. So how do we do that? So for the velocity, or horizontally now, so we know that from our proving, we know that velocity is constant all through. So let me quickly sketch the diagram. So I have to remove this part then so that we have a lot of space to explain in case it is confusing. Okay. All right. So this is our sketch. Back to our sketch here. All right. So if I were to ask for the velocity at this point, I have two velocities because my velocity vector is tangential to this part. And if it's tangential, it means I have one going towards the right, which is constant, and then I have one going up. So this one I can call it Vy, this one I can call it Vx. Remember, from vectors, for us to find vector V itself, what do we simply need to do? Square x, square y, take it under the square root, and then find the value of V naught vector. So that's what we want to do. So our Vx, so Vx, remember V naught of x is equal to V cos theta. So V naught of x is equal to V cos theta. And what is V? 30. So this is 30 cos 30. Huh? So 30 cos 30, what do we have? So let's press our calculator. So we have 30 cos 30. So we're having, so this is giving us 15 root 3 meter per second. So the final velocity, whether at this point, or at this point, or at this point, or at this point, will still be constant horizontally. So V final, V f of x will still be equal to rather 15 root 3 meter per second. So let's write this correctly so it doesn't get confusing. So 15 root 3 meter per second. Okay. Now, the vertical component, how do we find the vertical component? Remember, the vertically, so let's write that here, vertically, V initial of y is given as V sine theta. And what is V? That's 30 sine 30. So this is V naught of y. And if we press this in our calculator, we'll see that 30 sine 30 gives us exactly 15. So this is our initial velocity. Now, how about the final velocity on y? Then final velocity Vf of y will simply be equal to, remember, this is V sine theta minus gt. So this is equal to 15 minus what is j? 10. Then what is the velocity after 2 seconds? So 10 times 2. Okay, so 15 times 10, 10 times 2, so we have 15. 10 times 2, that's minus 20. And then v 15 times minus 20, 15 times minus 20. I say 15 times minus 20, 15 minus 20 rather. So this will give us minus 5 meter per second. So this is V final of y. So we've gotten the horizontal component. We've also gotten the vertical component. So what do we do? It's time to now combine to get the velocity at point 2. I know initially in our sketch, we assume that 2 seconds is this place. But you can see that this place, Vy is still going up. So definitely, it can be in this place after 2 seconds. Maybe to be around where the vertical component of velocity is already pointing downward. All right, so combining these two together, so we can say V naught vector now will now be equal to, or the magnitude rather, will be equal to the square root of V f of x squared plus V vf of y squared, and this will be equal to, so vf of x squared. So what do we have as f of x squared? We had 15 root 3, so everything squared, okay, plus vf of y, so that's simply 5 squared. So the reason I'm not using the negative sign is that it will return to, or it will still return a positive value after what's it called, squaring it. So pressing this in our calculator, so we want to do it one by one. So first of all, we write the 15 root 3, so equal to what, of course we have a sub, then you square it and square. So after squaring, we have so this should be equal to root of 675 plus 5 squared is 25. And by the time we add these two together, we have 700. So V naught, the magnitude, is equal to root 700. So sorry, yeah, root 700. And then the square root of 700, V naught, will simply be equal to the square root of answer, the square root of 700. So that's 10 root 7 meter per second. Now this is the velocity, or the magnitude of the velocity, just or after 2 seconds when it has been projected. But then from vectors, we know that the magnitude alone is not enough to describe the quantity. So eventually they ask for the direction. If this were to be a theory question, then definitely you want to find the magnitude and also the direction. But because this is simply um, what's it called? We don't know whether it is an objective question or a theory question, so we can actually leave our answer like this. But for the sake of this video, let's still try to get the direction. So we've gotten the magnitude already, that's 10 root 7 meter per second. So how then do we find the direction? So again, this is VFY, this is VFX. So I'm simply going to be taking the tan ratio. So we'll take the tan, so tan theta would now be equal to minus 5 divided by 15 root 3, and then theta will be equal to tan inverse of minus 5 over 15 root 3. So pressing this in our calculator again, so we have shift tan inverse, okay, of negative 5, okay, and then divided by 15 root 3. So our answer, the answer we're having is negative 10.89. Negative 10.89. Okay, so degrees. All right. So far, we've looked at the meaning of projectile motion. We've looked at how to solve questions underneath projectile motion. We looked at the different types of projectile motions that we have. So if you are still having any issues, so do well to let me know in the description section. So eventually you have a question that is still not clear, so do well to try and analyze it together and get back to you as fast as possible. If this video has been helpful to you, so please do well to like, share, and subscribe. So share to your friends, share to your loved ones, and then so we can both grow together. All right, thank you very much. So see you in the next video. Thank you. Bye.